Today, Doctor, we are from Group 11, and today we are going to present on noise reduction in audio signal by using FIR and IIR digital filter. To do this, we follow a simple 4-step process. First, we import the noisy audio. Second, we analyze its frequency spectrum. Third, we design our different filter. And finally, we use convolution to remove the noise and get a clean signal.
Hi, my name is Limzi. So first of all, we'll be using this code, which is to outload the noisy audio file into our MATLAB, and this will give us the discrete signal vector X and the sampling frequency Fs. And then we will be moving next to the discrete signal code, which is this. So the purpose is to visualize the raw digital signal, and which is the time domain representation. So we'll be plotting the first 100 sample using this stem plot function. So we can see that the individual discrete amplitude of each sample numbers. But it is very difficult to isolate or identify the specific noise frequency. So we will be moving next to the noise analysis, which is this code. So it is to remove the noise, but before that we need to convert the signal from the time domain into the frequency domain using FFT. So we'll be calculating the frequency vector F relative to our sampling rate. So we can get this magnitude against the physical frequency. So by looking at this graph, we can assume we can say that the dominance is below the 1000 Hertz. So from here, we can directly inform the cutoff boundary we need to set for our FIR filter design.
Moving on to the filter design, for the left hand side we have FIR for windowing, and the right hand side we have IIR for bilinear. So this is the method for the impulse response. The code we use is for the FIR is this. N is the order for low pass filter using Hamming window, while for the bilinear, NUMA is numerator, DINA is denominator, and Fs is the sampling frequency. So for the FIR windowing, we actually use the order of 15, and the right hand side IIR we use the order of 4. So why we do like that? Because actually the FIR didn't have pulse. As you can see, only the pulse at the origin, only one pulse. So we need more coefficient to obtain the sharp output. Therefore, higher order is required. While the IIR actually to achieve the same frequency, we need lower coefficient because the output depends on input and previous output. So lower order is required.
So moving on to the next part, although windowing and also bilinear are required only, but we also do every 5 of the filter, so to get the better visualization.
I'm Shenping, and I will be presenting comparison of our 5 implemented filter design. On the left, you can see the time domain waveform comparing the raw input signal to our 5 filter outputs. We implemented 3 FIR techniques using MATLAB: windowing with the FIR1 command, frequency sampling with FIR2, and the optimum technique. We also implemented 2 IIR techniques: IIR impulse variance and IIR bilinear transformation. Looking at the frequency spectrum on the right, it is clear that all 5 methods successfully achieve the core task of low-pass filtering the input signal, as the high-frequency noise has been effectively removed. Now here, in the frequency response plot, you can see the magnitude roll-off and, importantly, the linear phase response characteristic of the FIR design. Thank you.
Now we're moving on to our final step, which is the convolutions. We use the convolutions to help to filter our signal. So as you can see from the equations, we have Sn is our raw noise corrupt audio sequence, which is our input, and Hn is the impulse response, which is the structural footprint of our filter. So when we convolve them together, we get Yn, which is our clean filter output signal. Our system implements this operation using 2 distinct architectures. The first is the FIR filter. This operates strictly on current and pulse inputs, multiplying terms by specific width, which is the coefficients. It acts like a highly sophisticated smoothing average offering zero phase distortions. Secondly is the IRR filter. It introduces a feedback loop utilizing sparse input and sparse output. These recursive mechanisms allow our order for IRR filter to achieve an incredibly sharp cutoff with low latency and high processing speed. So, to make conclusions, collaboration is the mandatory block that transforms our abstract mathematical equations into clean real-world audio.
In conclusion, by using these filtering methods, we successfully remove the unwanted noise from the audio signal. The best choice simply depends on what your project needs the most. If you need a clean signal with a zero distortion, you should choose FIR filter. But if you need a faster processing and less delay, IIR will be the better option. Thank you for your time.